Welcome to The Explainer. Today, we're tackling something absolutely critical and honestly pretty fascinating in the world of structural engineering. We are looking at exactly how buildings are designed to survive massive, unpredictable earthquakes. Specifically, we're going to unpack the core differences between an OMRF and an SMRF. It's a topic that trips up a lot of folks, even seasoned professionals. But by the end of this, you'll know exactly how concrete and steel are engineered not just to stand tall, but to literally save lives when the ground drops out from under them.
Here's our quick roadmap for today. We'll start with when strength isn't enough, then look at the drunk man principle, dissect the anatomy of a plastic hinge, lay out the specific rules of SMRF, and finally, separate design fact from fiction.
Section 1. When strength isn't enough. A historical reckoning.
For a really long time, structural engineering had a pretty straightforward philosophy, right? Just build it strong. If a building had to hold up against gravity loads, dead loads, live loads, maybe some wind, raw strength was your only answer. You designed a rigid frame, you made it super stiff, and you walked away. But, well, nature is the ultimate stress test. Earthquakes like San Francisco in 1906, the Kilauea quake in '93 that claimed over 9,000 lives, and the devastating 2001 Bhuj earthquake where over 20,000 people were lost, these were massive wake-up calls. The engineering community had a deeply uncomfortable reckoning. We realized that perfectly strong, perfectly stiff buildings were just shattering. The old worldview of pure strength had completely failed us.
And that sparked a profound philosophical shift in how we build our world. It's perfectly captured by this quote from the IAT Master Lecture. "The frame that survives not by being strong, but by being wise enough to bend." I love that. Strength alone shatters, wisdom bends.
Let's move to Section 2, the drunk man principle, intuition over math.
Okay, before we get into the heavy math, let's just look at how people physically react when the ground shakes. Picture two guys standing in a hallway during a violent earthquake. Guy number one is a rigid soldier. Perfect posture, totally stiff joints. When the floor violently shifts, he can't flex his knees or ankles. He just topples over, catastrophically, with zero warning. That right there is our ordinary moment resisting frame, or OMRF. Now, guy number two, maybe he's had a bit too much to drink. He sways, his knees bend, he staggers, and grabs the wall. He looks completely ridiculous, right? But he absorbs the energy. He doesn't fall. That's our special moment resisting frame, the SMRF.
In engineering, this drunk man behavior has a name: ductility. Think about bending a piece of chalk. It's stiff, sure, but it snaps instantly without any warning. Now bend a piece of chewing gum. It deforms enormously, stretching out and absorbing a ton of energy before it finally pulls apart. In seismic engineering, we desperately want our buildings to act like chewing gum under extreme stress, not chalk.
So, here is the multi-million-dollar question. What actually happens when an earthquake is so severe that it pushes a building past its elastic limit? Well, an OMRF, acting like that chalk, suffers a sudden, brittle failure. The building collapses before anyone inside can even react. But an SMRF? It's designed specifically for this exact nightmare scenario.
Which brings us to Section 3, anatomy of a plastic hinge, the sacrificial hero.
To force a massive concrete building to act like chewing gum, engineers actually have to build in a deliberate, sacrificial, weak point. Enter the plastic hinge. It's basically a hero built right into the concrete. It's a highly engineered zone in a beam that is allowed to yield, rotate, and permanently deform. It literally eats the earthquake's shockwaves. The beam degrades, yeah, but it does not snap. It takes the punishment so the rest of the building survives and everyone inside has time to get out safely.
But you have to control exactly where these hinges form. And this is the absolute golden rule of SMRF design, the strong column, weak beam principle. You must design the frame so the beams yield before the columns do. Think about it. If a beam sags, the floor above is still held up by the columns. But if a column snaps first, you lose all vertical support and you get a catastrophic pancake collapse. Strong columns, weak beams. Non-negotiable, always.
Let's see how this works in practice in Section 4, the rules of SMRF, translating physics to code. How do we translate this physics into the actual rulebook? In India, IS 1893 handles design forces and IS 1390-20 handles ductile detailing. The code assigns what's called a response reduction factor, or R factor. For an OMRF, that number is 3.0. Basically, the code knows this building only has moderate ductility. It can't absorb much energy, so you are legally required to design it to withstand much higher raw seismic forces. but switch to an SMRF, and that R factor jumps to 5.0. That is a massive shift. The code actually lets you design the building for significantly lower lateral forces on paper. Why? Because you're making a promise that your building will absorb that energy through extreme ductility. But to legally make that promise, you have to follow some incredibly strict detailing rules.
Enter IS 139020. Here's exactly how you turn concrete into chewing gum. First, you pack steel stirrups incredibly close together near the column face. This traps the concrete so it doesn't just crush when the hinge rotates. Second, absolutely no lapse places in the plastic hinge zone. Rebars fighting for grip there will literally just unzip catastrophically. Third, columns have to be robust, at least 200 millimeters thick, with special ties. And finally, you have to heavily confine the beam column joint, because if a joint fails, it's game over for the structure.
And we don't just guess that we have a strong column, weak beam, we prove it mathematically. The code demands a mandatory check at every single joint. The sum of the moment capacity of the columns must be at least 1.1 times greater than the sum of the moment capacity of the beams framing into that exact same joint. This math forces the hierarchy of yielding. It guarantees the beams will give out before the columns ever do.
Section 5. Design fact versus fiction, clearing the confusion. There are some really dangerous misconceptions out there that trip up a lot of students and even seasoned professionals, so let's clear the air right now. Here is the biggest myth of all. An SMRF is stronger than an OMRF. Guys, this is completely false. An SMRF is not about raw ultimate strength. In fact, because of that higher R factor of 5.0, its elastic strength on paper might actually be lower than an OMRF. The reality is, the SMRF survives because it's infinitely more ductile. It survives through deformation and energy absorption, not by acting like a rigid brick wall.
So where are we actually using these? Well, in low-risk areas like Seismic Zone 2 in India, an OMRF is perfectly fine. But after the horrors of Bhuj, the rules rightfully changed. In Zones 3, 4, and 5, the high-risk zones, SMRF ductile detailing is now absolutely mandatory for reinforced concrete. And what's the cost of this safety? Implementing SMRF detailing only adds about 8 to 15% more steel rebar. For that tiny premium, you reduce the risk of structural collapse by a massive order of magnitude. It is literally the best investment in life safety you can make.
Putting them head-to-head, the contrast is super stark. OMRF relies on an R factor of 3.0, moderate ductility, and basically hopes it's strong enough. SMRF steps up with an R factor of 5.0, strict splice bands, and legally mandates that strong column weak beam math under IS 139020. It's the difference between hoping a building is strong enough and guaranteeing it's wise enough to bend.
Which leaves us with one final thought to chew on. If a mere 8 to 15% increase in rebar can transform a building from a fragile, rigid soldier into a resilient, staggering survivor, why would we ever design differently when lives are on the line? It's a pretty incredible testament to the value of seismic ductility. Thank you so much for joining me on this explainer. I hope this completely changes how you look at the concrete giants all around you. Keep questioning, keep learning, and I'll catch you in the next one.